Okay, so moving on. So now I'll just go over a little bit of this using a function of two variables. Just hopefully that'll help see something concrete. This is about as big as it can get while it still makes sense on some slides. So a function of two variables, we can think of it as f of xy, and then the notation I introduced in the last section, I'll just say that's from R2. So xy would describe a point in the xy plane. And then f of xy is going to assign one particular value to each point in the xy plane. And so that would be R. So you could think of it as z maybe equals f of xy. And the partial derivatives of f are also going to be functions of x and y. And so this is how we would define them. So the partial of f with respect to x, it's a function of x and y, so that's why I've put this xy here. And it's just going to be defined as the limit. So here, when I'm taking the derivative with respect to x, I'm just going to add a bit to the x argument, and then subtract away the value at my point, divide by h, so that the distance between the 2 points where I've evaluated the function, and then take the limit as h goes to 0. So that's exactly the same as the definition of the derivative, except that you just have this extra y hanging on here. And then we do exactly the same thing for y, so this time I'm just adding the perturbation to y, and so that's going to give me the partial derivative with respect to y. And then the gradient of f of xy, so I could write that as d. So d here is an operator. So the difference between an operator and a function is the output of a function is a number. Here, the output is going to be a vector of two functions. So the output is actually a function of x and y. And so instead of calling d a function, I'm going to call it an operator. So the output of an operator is a function. And then the Hessian is just going to be made up of, and yes, I actually did it right, the four sort of mixed partials, although the ones on the diagonal are sort of hidden or in disguise, because even though they're a mixed partial, they're the same thing mixed with itself. But they're also each going to be functions of x and y. And so now let's look at an example. So suppose I define my function to be x squared y cubed, and I just want to compute both the gradient. So df is going to be the gradient, and d squared f is going to be the Hessian. And then I want to evaluate them at the point 1, 2. And so remember, well, let's see if I... So if I was going to try and find the slope of a function just using a function of one variable, when I take the derivative of my function, I get a function. So if I have a function of x and I take the derivative, I also have a function of x. So I'd have f prime of x. And then suppose I want to know what is the slope of f of x when x is equal to 3. I just evaluate the derivative at the point x equals 3. It's definitely a mistake to evaluate the function at 3 and then take the derivative, because you would get 0. And so for some reason, everybody seems to understand that with a function of a single variable. But then they go ahead and make that mistake very often when they start working with multiple. So for instance, when I ask you to evaluate it at the point 1, 2, they'll calculate the gradient correctly, evaluate that at the point 1, 2, and then try and take the derivative of that again. And the moral is you have to take all of the derivatives before you start evaluating. So here I've just skipped most of the work. I think I just put the answers here. So some of these are really easy to see. So the partial derivative of x squared y cubed with respect to x is just going to be 2xy cubed. It's also easy to see that the partial derivative with respect to y will be 3x squared y squared. It's just the power rule and treating the other variables, so in this case y, in this case x, as a constant. And then we have to compute the mixed partials. So here I have the partial of f with respect to x squared. And so I already know what the first partial is with respect to x, so I can just plug that in here. And then I need to take its derivative one more time with respect to x, so I get 2y cubed. The actual mixed partial, so here dy then dx. And again, I've already computed the derivative of f, or the partial derivative of f with respect to y, so I'm just going to recycle that result rather than do it all over again. And then of this function, I'm going to take the derivative with respect to x, so I get 6xy squared. And then by the theorem I had, so I hope nobody did both partial derivatives for the quiz question, because that was a well-behaved function, so you could have just taken one and then said by the theorem the other one has to be equal to that. So I'm going to do that here. So this is a well-behaved function. I can take derivatives of a polynomial indefinitely. At some point I hit a constant, and then I take the derivative of that, and I get 0. But 0 is still a valid function, so I can continue to take the derivative of that indefinitely, and it just stays 0, but it's still differentiable. Oops. And then I just have to calculate the other second-order derivative, this time with respect to y. And again, I'll just recycle the first partial with respect to y that I've already computed, take that's derivative, and so I get 6x squared y. Oh, and I guess I put in sort of my hidden light gray color here, that this is equal to the other partial derivative, other mixed partial derivative. So now I'm just going to plug these into the gradient. So the definition of the gradient is just the partial of the function with respect to x and the partial of the function with respect to y. So I can just plug in those two partial derivatives that I computed on the previous slide. And then if I want to evaluate the gradient at the point 1, 2, so here I have 2 times x times y cubed. So this is 2 times 1, so that's just this one right here, times 2 cubed, so that's just this 2 here. And then 3x squared y squared, so 3 times 1 squared times 2 squared, and easy enough, 16, 12. And then I'll do exactly the same thing for the gradient, for the Hessian. So first I'll just plug in the formulas that I computed on the previous slide, and remember we get this symmetry of the off-diagonal entries in the Hessian. And then when I want to evaluate the Hessian at the point 1, 2, I just plug in 1 for x and 2 for y. And so this gives me the actual value of the Hessian, but only specifically at the point 1, 2. If I move away from 1, 2, then these numbers here are going to change. And so I guess where we're going to be using this is when we get to solving problems numerically. We'll be computing the gradient and the Hessian. And then that's going to give our algorithm some idea. So based on what these numbers actually are at a certain point, we're going to try to move to another point. So we'll move maybe from 1, 2 to 1, 1. And the way we're going to choose where we're going to move is going to be a function of these actual numbers that appear in here.